Welcome to video number 2. We're going to do one more direct comparison test to make sure we understand what the big idea is. And then we're going to go into the partner of direct comparison, which is the limit comparison test. Both of these tests can help us determine convergence or divergence if we have a second series to compare to. So in this setup, I'm going to look for a comparison, a buddy series, if you will. And I notice there's a lot of things going on here. Why don't I just say this is 1 over 7n squared? Now, if I look at this carefully, I guess I could factor out the 1/7. And I don't have to show this. I'm just doing this so that you can see, oh, eventually this is going to turn into a p-series. A p-series where p is equal to 2. And the p-value is bigger than 1, so it is going to converge. Okay, but now I have to compare the one I just found with the original one. Which is the bigger one? Which is b sub n? Well, when I look at the denominator, this is 7n squared plus 4. This is 7n squared. So this denominator is bigger. But when the denominator is bigger, the fraction as a whole is smaller. That means this is the bigger function. I'm sorry, the bigger series, or the series with the bigger terms. And therefore, if this bigger one converges, then the smaller one has to converge as well. And I can write that and say this converges by direct comparison test. Now, again, we have to find a buddy series whose outcome we know, and we have to be able to compare it directly with the other original series. Sometimes that's not possible. And so for that, we use the limit comparison test. Because the limit comparison test, we don't need to know which one's the bigger one, which is the smaller one. We just need two series whose terms are positive. So I got to make sure the terms are positive. And then I take the limit of one of the terms, of the ratio of the terms. And as long as my limit value is a finite positive answer, then I know both of these series behave the same way. So I'm going to say that again. With the limit comparison test, we take the nth term of one limit and put it as a ratio to the nth term of the second series, and we take the limit. If we get an answer, if we get a finite positive answer, then both of these behave the same way, which means I kind of need to know at least what one of them does, because if there is a limit value that's finite and positive, the other one's going to behave the same way. So I guess I'm basically saying they're either both divergent or both convergent. That's what I mean by behave the same way. So I still have to look for a buddy series. So all comparison tests, I need a series to compare it to. I need that secondary buddy series to compare it to. This is saying take the limit of the nth terms, and if you have a finite positive value, then if you knew what the buddy series was going to do, the original series is going to do the same thing. And that certainly helps with situations like number 4. Now, number 4 looks really complicated, right? And so what we're going to do is we're going to find a buddy series for this. And again, we're going to peel away kind of everything except maybe the initial terms. So the leading term on top and the leading term on the bottom of the fraction here. So this is what I have, which I guess can also be rewritten as 1 over n to the third, right? N squared, n to the fifth, I can cancel or reduce 2 of these n's with 2 of the n's, and I'm left with 3 n's on the bottom. Hey, this is a p-series. It's a p-series where p is equal to 3. That's bigger than 1, so I know that this converges. Awesome. So what we're going to do is we're going to take the limit. I'm not going to sit here and figure out which is the bigger one, which is the smaller one. It's going to get really complicated with all these terms. So I'm just going to take the limit as n approaches infinity of the first term divided by the second term. But that would mean I have a fraction divided by a fraction. So instead, I'm going to think of it as the first term multiplied by the reciprocal of the second term. And I'm going to use this 1 over n to the third. So I'm going to multiply by the reciprocal of that. And I'm going to figure out what happens here. Well, I guess I can multiply this out. This will be the limit as n approaches infinity of 2n to the fifth minus 2n to the third, all divided by 5n to the fifth plus 3n plus 1. And if you remember, when we were taking limits as n approaches infinity, we're really just worried about what the leading term is doing. So really, this is the same thing as the limit as n approaches infinity of 2n to the fifth divided by 5n to the fifth. You could also do L'Hopital's rule and take the derivative of the top over the derivative of the bottom, but you would have to do that multiple times. So instead, we focus, since n is approaching infinity, the leading term in the numerator is going to determine the top, and then the leading term in the denominator is going to determine the bottom. But it just so happens that, look at this, I can reduce the n to the fifths, and I'm left with 2/5. That is a finite positive answer. And if it is, that means the original series will behave however the new series behaved. And the new series converged, so therefore, let me make it a little bit smaller here. Therefore, my new series, 2n squared minus 2 divided by 5n to the fifth plus 3n plus 1, converges. Let's make it a little bit nicer looking. Converges by limit comparison test. It's all good. We took the limit of one nth term divided by the other nth term. And when I did that, I took the limit and I got a finite answer. Now, some of you might be wondering, hey, I thought there was a 2/5 here. You didn't include the 2/5 here. I could have. And if I had, I don't think it would have changed much other than when I got to this point, it would have changed it to 10, and this would have been 10, and then this would have been 10 and 10, and this would have been a 1. It still would have been finite and positive. It still would have worked out. So what's the key with the limit comparison test? You still need a buddy series. You need to know what that buddy series, the outcome of the buddy series, is it convergent or divergent, and then take the limit of the buddy series in the original one. And if you get a finite positive answer to the limit, well, then they both behave the same way. If the buddy series converges, the original one converges. If the buddy series diverges, the original one diverges. So we're going to do that one more time in this video, and then we'll pause. Can I find a buddy series for this? Can I find a partner series for this? The easiest one would be 1 over n squared. Why would I choose that? Well, because this has 3 terms, but this is the leading term, so that kind of determines what's going to happen. If you want, you could even do 5n squared, right? But I'm going to make it easy, and I'm just going to do this. I recognize this as a p series. P is equal to 2, that's bigger than 1, and that's going to converge. Great, now let's take the limit. I'm going to take the limit as n approaches infinity of the original one divided by the new one, but dividing means multiplying by the reciprocal. And so I can do this. I'm going to take the limit as n approaches infinity of n squared over 5n squared plus 5n plus 5. And again, if you remember your limit taking, when we're taking the limit as n approaches infinity, we focus on the largest term in the numerator compared to the largest term in the denominator. And that's going to reduce. I'm left with 1/5. That's finite. That is positive. So therefore, they're going to behave the same way. And if my new one converged, then the original one is going to converge as well. So this will converge by the limit comparison test. I'll be honest, a lot of people, including myself, prefer to do the limit comparison test to the direct comparison test. You don't have to sit there and wonder, wait, which can I show that one is bigger than the other, and then go through all that process. Just find one that kind of looks like it. Make sure you know what the outcome of this new one is, and then take the limit of one divided by the other, I usually do the first one, original one, divided by my new one, and then take the limit. And if your answer to the limit is a finite positive number value, then they're going to behave the same way. So if this one converges, that one's going to converge as well. Welcome back. In the next video, we'll kind of wrap up the comparison tests before we get into the other tests.